So write the reaction between an aqueous solution of hydroiodic acid and sodium hydroxide. Well, we have hydroiodic acid reacts with sodium hydroxide to form sodium iodide, which is soluble in liquid water. And that is a precipitate, and therefore this is a double displacement reaction. We have barium chloride reacting with magnesium sulfate. We produce the precipitate, barium sulfate. It's actually really important that that's not soluble, because barium is crazy poisonous to people. However, we use barium sulfate to image people's intestines. You'll drink a milkshake made out of this stuff, and that allows radiologists to get good data looking at a person's swallowing, or their esophagus, or their stomach, or their small intestines, or their large intestines. You can pretty much view the whole alimentary canal from lips to anus with this material. And it only works because it's not soluble, so it never actually gets inside of a person. You drink it and it goes through your body, but then it comes out of your body and it never breaches the first cell layer, so it's never technically inside your body. Potassium phosphate and barium chloride, and we produce barium phosphate, which will precipitate. And then they have to balance the equation. You have 2 phosphates on the left, 2 phosphates on the right. 6 potassium on the left, 6 potassium on the right. 6 chlorine on the left, 6 chlorine on the right. 3 bariums on the left, 3 bariums on the right. You have a nice balanced equation. Ammonium chloride reacting with sodium nitrate. In this case, there's no reaction because nothing precipitates. Even if they switch partners, that gives you ammonium nitrate and sodium chloride, and they all just stay dissolved. So literally all the ions just stay dissolved. There's ammonium pluses floating around, chloride minuses floating around, sodium pluses floating around, and nitrate negative ones floating around. But because nothing precipitates, we don't form any gas, we don't form any liquid, we don't form any solid. Literally everything stays aqueous. We consider that no reaction for a double displacement reaction. Heat in chemical reactions. Chemical reactions either absorb heat or release heat. So, an exothermic reaction releases heat. This is like burning fuel or burning wood. Energy is a product. You're producing energy and it's escaping. Where that's an exothermic reaction. Whereas an endothermic reaction that absorbs energy, you have to put energy in. So cooking a steak is endothermic. You have to apply heat to your steak to cook it. And cooking is a set of chemical reactions that occurs, and so you'll notice cooked food is very different than raw food. If you don't believe that, take a bite of a baked potato and then take a bite of a raw potato and see what happens. And you'll see that they're very different because the chemistry is changed by cooking it. So exothermic reactions, they release energy. Energy is a product in an exothermic reaction. In an endothermic reaction, energy is a reactant. It reacts. You have to supply it. And so in endothermic reactions, you have to purposely supply the energy. In an exothermic reaction, it just is produced as a byproduct of the reaction. Here's an interesting endothermic reaction, because this is one of the pollutants from cars that you can't control with the fuel. Because the atmosphere is already 78% nitrogen and 21% oxygen by mass. So really the atmosphere is like 99% nitrogen and oxygen. So if a surface gets hot enough, these two will react and form the nitric oxides, which can then contribute a little bit to nitric or to acid rain, because they can combine with water to form nitric acids. And again, that has nothing to do with the fuel you're using in your vehicle. It just has to do with the fact that if the engine gets hot, the nitrogen and the oxygen that's naturally in the atmosphere can react to form nitric oxides. Heat of reaction is how much energy is produced in the chemical reaction. So if I burn 1 mole of carbon, like a brick of charcoal in my grill, with 1 mole of oxygen gas, I produce 1 mole of carbon dioxide gas, and I release 393 kilojoules of energy. which is why burning charcoal can be used to cook food in my grill, because it's an exothermic reaction. Heat is a product, and I can use that heat to cook a steak or cook a hamburger. In the reaction, hydrogen gas reacts with iodine solid plus 12.6 kilojoules to produce 2 hydrogen iodides. Is this exothermic or endothermic? Well, look where energy is. Energy is on the left side of the arrow. So your energy is on the left side of the arrow. That means energy is a reactant. This is an endothermic reaction. It's absorbing energy. And if you produce 4 moles of HI, you'll double the energy involved. So the energy is proportional. If you triple the size of the reaction, you triple the energy needed. And again, we'll go back to that next chapter in stoichiometry when we look at the proportionality of all the reactants and all the products. Photosynthesis, great example of an endothermic reaction. Energy is a reactant. It's on the left side of the arrow. You need the sun shining to do photosynthesis. With no sun, you get no photosynthesis because you lose the energy. And that's a key ingredient in the reaction. You need that as a reactant. And in photosynthesis, 6 carbon dioxides and 6 waters combine to form a glucose and 6 oxygen molecules. And so again, the net products of photosynthesis is the plant fixes organic sugars and releases oxygen gas to the atmosphere. All oxygen gas in our atmosphere comes as a byproduct of photosynthesis. So this is why the Earth has 21% oxygen in the atmosphere. It was all made in a photosynthetic organism doing photosynthesis. In the very first step of photosynthesis, a high-energy electron is ripped out of a water molecule, oxidizing it to oxygen gas, which is released by the plant, which is good because then we need that oxygen to breathe it. So again, photosynthesis is endothermic. The energy is supplied by sunlight.